B part 4, lecture 6, Hamiltonian dynamics. Now, constant of motion. You see, all these concepts about Hamiltonian dynamics, we can apply in classical physics, classical mechanics, and electromagnetism. You see, that's a very important tool, and you see why it is important, okay? All this concept, constant of motion and symmetry, okay? That's a very, very, very crucial, okay? It plays an important role in this area which I mentioned. So let's define of is constant of motion, C.O.M. Suppose a non-autonomous system where F is a function of Q of t, P of t, and t explicitly. You see, non-autonomous means explicitly. See, any function. So you just substitute, okay, this P, this Q and P by its coordinates, okay, generalized coordinates and generalized momenta, P. I is from 1 to n. So the differential, just a calculus, okay? This is, you can read over here, because F is a function, in this case, of t, q, and p. Or df by dt, that's a total time derivative, okay? This is just divide the right hand side, you see, dq dt, dp dt, in which, from the Hamilton's equation, you see, we can substitute, okay, this derivative here, okay, by the respective Hamiltonian. So this partial h with respect to p, and this is minus partial h with respect to q. So I can write exactly, okay, this part over here, I can represent it as the curly bracket, the Poisson bracket between F and H. You just see here. You see the definition involves the partial derivative. You just substitute this F and H. In general, in the beginning, this is capital A and capital B. So that's this attention. This is non-autonomous. Okay. Now, thus attention, you come over here. Whenever you have a quantity F moving along a Hamiltonian flow, okay, that when it moves in the space, they say the phase space. You see, this moving, okay, through out the phase space Q of t, P of t. That's what I call, okay, the phase space. Phase space. You see? Then I just write df dt. This is the Poisson bracket between f and h plus the partial derivative, okay? This is for non-autonomous. And a constant motion satisfies that the definition, it's better to set this. You see, this is a sign of definition. So you define a constant motion, okay, just this right hand side setting to 0. Attention now, the trajectory, okay, is a special values of P and Q. You see, there's a trajectory. In this trajectory, that where if this constant of motion is defined, in this trajectory is equal to 0. So, now, on the other hand, how the total derivative, okay, the h here is energy, okay? You just see h is energy just from here. You see, h is equal the kinetic energy, okay, which energy plus potential energy in this case. Just when we derive the Euler-Lagrangian, okay, equations. So this how the total derivative changes along a trajectory. You see, the trajectory it's a special relation between Q and P, okay? Could be a curve, okay? But in n-dimensional space, this is not actually a curve, okay? You just you set here a special, so the trajectory, okay, the total derivative here, how it changes. So substitute f by h leads to, again, now I want to impose my f be the Hamiltonian, you see? So you just substitute, it's quite easy. Now dA, instead of df of dt, you see, I just plug here h and h and h. So it's quite easy. You just look at here and copy from here. So in this case, okay, this term over here will cancel with this one. So dH of dt, the total energy, the derivative of total energy with respect to time, will be to equal the partial derivative with respect to time. So recall that H is a total energy, just for you to remember. T is kinetic energy, V is the potential energy. This comes from the definition of L is T minus V. And you remember that we applied the variational calculus just to derive, okay, the Hamiltonian. Okay, now, so if the Hamiltonian does not, you see in red here, explicitly depend on time, the total energy H, in this case, is called conservative, okay, along the path, the phase space. Attention now, only along the path, okay? In another point, this cannot be true. So that's important emphasis, which I'm saying to you. So repeating, okay? Now, in this case, you see here that we call that, and then I write down just over here. Now, since if the Hamiltonian does not, you see, explicitly depend on time, then the total energy H is conserved along the phase space, okay? The trajectory phase space, motion. That's a motion because P and Q depends on time. So, but now, if it does not, if it does, the total energy can change, you see, due to, in this case, okay, some external agent, okay, that's important, okay, along the time. So that's important. If it does, okay, there is an external agent which make the Hamiltonian to this case, the derivative of this that exists. So this will be different, okay, if it does. If it does not, if it does. So this I remark here, okay, does not means the total derivative is equal to partial derivative, okay? So the total energy is conserved. Then you see external agent, okay, is acting just to implies, okay, that the h of dt is not equal to the partial derivative, okay? In this case, okay, does not means equal, does not, does means different, This is different. So there is an external agent. Now, next lecture 7, definition of symmetry. That's a very, very, very crucial, you see, concept in Hamiltonian dynamics. Okay? That's very, very crucial. Okay?